Hello, it is Tuesday, April the 7th, and we are ready for science. If you notice the next page in your book, page 222, gives you an activity. It talks about making a sound slide. If you would like to do that, I would encourage you to do that. Um, I was looking around my house, couldn't find a rubber band. I used some other things. I used a hair band and some of those stretchy bands all linked together, but they didn't make the same sound. So if you'd like to see if you can locate a rubber band in your house and a ruler and a little cap, you can make this little sound slide. And what you're doing is you're listening for the different sounds depending on where the cap holds the rubber band down. It's the same idea of when you play guitar and you press down the strings. Depending on the strings you're pressing down, you're making a different sound. When little kids pretend to play the guitar and they just hold their hand like this and do this, that's not accurate, is it? You are pressing down on different strings so that you are making it sound differently each time, and it's affecting the sound on how you're holding those strings down. So that's just what the sound slide is demonstrating here. And if you would like to make one of those, I would encourage you to do that. But we're not going to fill out those pages together, and you don't have to do that because I know that some of us may have difficulty in finding different things around the house. But what we are going to do is move on ahead to page 224 to 227 and talk about the characteristics of sound. Today we're going to talk about the characteristics of sound. And if you look in your activity manual, you will see this page next, and it's just a blank page, but at the top it says characteristics of sound. And it says make your own organizer for the characteristics of sound. So what we're going to do is we're going to make our own graphic. It's called a graphic organizer so that we can organize our notes and understand what we're learning. So I've started you here, and in the middle, you're going to, so in the middle of this page, you're going to do a big circle right here, and we're going to say characteristics of sound. And in our reading today, we're going to learn about three different things. Pitch is on one side, volume, and then the one down here is quality or timbre. Okay, quality or timbre. But you just need to start with these right now, and we'll get to each one, and I'll make sure you can see the different parts of the graph. There, we can make it a little bit smaller so that we can see it. Okay, so you're going to put that on your page and stick with me as we go through this section, okay? So let's look at it together. Characteristics of sound. This is page 224. Sound engineers understand and use the characteristics of sound. In a similar way, the characteristics of sound help us compare and describe individual sounds. You experience many different sounds each day. A songbird trills a high, happy song. The horn of a tugboat makes long, low blasts. The siren of a police car may change between loud and soft sounds. So we've said before, the words that we use to describe things help us to organize things. We have to label things in order to know how we're all talking and what we're all talking about. So that's why we have to label these different characteristics of sound. So the first one we're going to talk about is pitch. Pitch is how high or low a sound is. So we've got pitch here, so let's make sure that we put the definition over here to the side. So you can make another circle coming off of this if you want. I'm just going to write, I'm going to make it smaller. Okay, so how high or low a sound is. Okay, how high or low a sound is what pitch is. Okay, so here's another thing. The very next sentence says the pitch of a sound is related to its frequency. So that's something else I want to put. So let's make sure we write that down. Related to its frequency. Okay, so how high or low a sound is, and it's related to its frequency. Remember that the frequency is the number of waves that pass a point in 1 second. These waves result from vibrations. A slowly vibrating object has a low frequency. Okay? I'm going to put that over here. Slow equals low. And then fast equals high. So slow and low, fast and high. Okay? A slowly vibrating object has a low frequency. This produces a low pitch. As an object vibrates faster, its pitch gets higher. Okay? You can hear changes in pitch, for example, by listening to the different sounds made by an electric mixer. So if you go to your mom's mixer and turn it on and you start slow, it'll have a rrr, and then as it gets high, it goes, ah, it gets a little bit higher because it's going faster. Now, I know you've done this before, and if you'd like to do this yourself, you can. I know you've probably experimented with this before, but I have some glasses here. This one I filled all the way almost to the top with water. This one is about halfway filled up, and this one is low, okay, less than half. So what's that, probably about a third, okay? So let's figure out which one is going to have the high pitch. So if it vibrates fast, it's going to be high. If it vibrates slow, it's going to be low. Well, what will the water do? Let's see. Do you hear the difference? So which one is lower? The one that's full of water, right, is low. So why do you think that the vibrating is going slower if it's lower? What's causing it to slow down? Do you think all that water is causing the vibrations to slow? Now, if I put my hand on it, do you think I'm keeping some of those vibrations from happening? Whereas if I just lay it down, okay, I'm not slowing those vibrations down by putting my hand over it. Okay, so high, it also depends on what you hit it with. Let's change it. I had this kind of dull, heavy knife. Let's hit it with the tip of this scissor and see if it'll change it a little bit. Still sounds about the same, doesn't it? But you can hear the difference in pitch between them, can't you? So that water is slowing down the vibrations, and that's why it has a lower sound. Okay, let's move those out of the way so I don't spill it. Okay, so now, God gave the human ear the ability to hear certain frequencies. Most people can hear sounds with frequencies between 20 and 20,000 hertz. The lowest note or pitch on a piano has a frequency of about 27 hertz. The frequency of the highest note on a piano is a little over 4,000 hertz. That's a big difference on the piano scale, isn't it? The pitch of most sounds is a blend of frequencies. Some creatures, such as bats, dogs, and insects, can hear higher frequencies than humans can. If you blow a dog whistle, you cannot hear the sound, but a dog nearby can. Okay? And then it says there, when musical instruments play together, they must be tuned to the same pitch. If they are not, they will produce sounds that clash rather than blend. The standard pitch used today is not the same as the ones musicians used in the past. The tuning fork of the 18th century composer George Friedrich Handel tuned the A above middle C to the frequency of 422.5 hertz. Today, the same note is usually tuned to 440 hertz. That's interesting. So it's tuned a little bit differently. Okay, so it's measured in hertz. And it gives you a chart there at the bottom, the hearing ranges. So from human to the scarab beetle. So who of all of those things, who can hear the lowest, let's say it this way, who has the smallest range of hearing? And that would be the parakeet, wouldn't it? Okay, but look at the porpoise. Wow, almost off the charts, all the way from low all the way to high. Okay, now let's turn the page and look at 226. Now this is volume. Volume, okay, so let's change my color here and get ready to talk about volume. Volume is how loud or soft a sound is. So, how loud or soft, how loud, I didn't change my color. How loud or soft a sound is. Okay, that's volume. Loud or soft. Pitch, high or low. We want to get these terms right, matched up to the right thing. The volume of a sound changes as the amount of energy used to make the sound wave changes. So this has to do with the amount of energy that is exerted. A greater energy or intensity will produce larger vibrations. Large vibrations make louder sounds than smaller vibrations do. Do you think that's important? Let's say that. Let's say large, changed my color again, didn't it? Vibrations equal louder sounds. And we can see that on an oscilloscope that we talked about the other day that kind of measures and shows sound. Okay, there are times that you may try to walk quietly through a room. So think about what you do when you walk quietly. You don't want your foot to land very hard, right? You're wanting it to be soft. So your larger vibration that you make, the louder the sound. The intensity of a sound is measured in decibels. So let's say that too. We want to make sure we have that. Measured in decibels. And the decibel is actually named after Alexander Graham Bell. Remember, he had so much to do with sound and the telephone, and so the decibel is actually named after him. The sound of your breathing is about 10 decibels. Talking in a normal voice to your friend is about 60 decibels. The sound of a jet taking off is about 160 decibels. So look at your chart there. You go from kind of the pinky white 0 threshold of hearing, and then it goes to normal breathing, that's 10, a whisper is 20, a home is 30. Suburban means outside of the city. If you're an urban home, that means you're New York City. It's louder there, isn't it? And then you go up and up and up in your decibel levels, and at the very top we have a rocket engine at 180. Says the human ear can be damaged by too many large, loud vibrations. Now think about it. If sound is vibration, and you've got that vibration hitting your ear every time, that's how it's damaging. Okay? Because it's vibrations that's hitting your ear. Because sounds cause your eardrum to vibrate, the force of strong vibrations can cause pain. Exposing your ears to intense sound for long periods of time may reduce the ability of delicate structures in the inner ear to sense sound. So you actually dull those. This may cause hearing loss. A sudden sound, such as a firecracker going off, can cause temporary hearing loss. You should wear hearing protection anytime your ears are exposed to very loud sounds. Now, the third characteristic of sound we're going to look at today is quality or timbre. Quality or timbre. So let me, whoops. Ooh. Now, let's go up. There we go. Quality or timbre. Timbre is the quality of a sound that distinguishes it from other sounds of the same pitch and volume. Okay, so this sometimes can be referred to as, I think this is interesting, the color of the sound. Meaning, what was my other color up there? Green. So that what makes it unique. This is what makes it different than other things. It's more than everybody can still be on the same pitch and the same volume, but there's something different. Think about an instrument. The oboe and the violin, they sound differently even though they could be on the same pitch. So it's the color of the sound. It makes it different. It's what makes it different than the other sounds. That's the quality is its uniqueness. Okay? Before a band concert, the instruments tune to the same pitch. However, the trumpets sound different from the clarinets. So that's what I just said. Your different instruments sound different, even though they're all on the same pitch. Most of the sounds we hear are a blend of sound waves. Each of these waves have different characteristics. As these waves blend, so think about sound as this, all those waves coming together. The sound has a certain timbre. If one sound wave is added or removed, the timbre will change. A clarinet has a reed that vibrates. The reed is not the only part of the instrument that vibrates, though. A clarinet is called a wind instrument because it uses a reed. When a musician blows into the clarinet, the long tube that forms the instrument vibrates as well. The air inside the clarinet also vibrates. A skilled musician must control all the vibrations so that they blend to produce a pleasant sound. An oscilloscope image of a single pure sound, such as that made of a tuning fork, looks smooth. Musical instruments, however, do not have a pure sound. Instead, musical instruments produce sounds that are a blend of different vibrations or sounds. On an oscilloscope, okay, the instrument that makes the sound waves, these blended sound waves look rough and wiggly. You recognize many sounds without thinking about it. You may be playing in a backyard with a group of friends. When someone's mother calls from the house, you know immediately whether it's your mother, right? Could be the same pitch, same volume, but you know from the quality of her voice who it is. The timbre of her voice helps you know who it is. Okay, so we've got our graph here, so you've been able to do this side. Now, I want you to quickly look at this side today. This will give you a really good review on what we talked about today, and you'll be able to identify and make sure you're using what we did together to figure out the different answers to these questions on this side. Okay, so both sides, we did this side together. It's completed now. Now you're moving on to the questions and make sure you can answer those. In the comments below, here's your extra part to this. I want you to pick one animal that is not listed on page 225. Okay, so not a bat, cat, dog, elephant, one that is not listed. I want you to pick any animal, and I want you to look up its hearing range. Okay, so it says frequencies, so look up hearing range of whatever you pick, and then tell me what it is. Like a bat has a range of 100 to 120 hertz. So see if you can find another animal, any animal, and tell me its hearing range. That's what I want to see in the comments below. Okay? All right. Get busy.